Okay, so the last thing I wanted to talk about before, is just this idea of curvature. So the textbook relates DTDS, which we just talked about, as being a vector which points, so in the circle at least, it points toward the center of the circle, but it points tangent or perpendicular to the normal vector. That's kind of interesting. But it turns out that the length of that vector is actually significant, and it's curvature. But there's a way to visualize that, which I think is really helpful, which the book didn't talk about. So let's say that I wanted to find the curvature. I wanted to think about the curvature at a point A, and you can see the point A is on my spiral right there. Okay, so I have my point on the circle, on the spiral, on this curve, and I'd like to know how the curvature, or how curvy it is. And if you look at this, you might think of it's sort of like a circle. So we might think, okay, well, if we could just talk about the radius of that circle, we know that we can sort of visualize in our heads how curvy something is if we can think of its radius. If it's a circle and its radius. So I know that something that has a radius of zero point 0.1 is a very tight circle, and I know that something that has a radius of 1,000 is a very soft, gentle curve. So we can think of curvature in terms of circles, and that's actually a very natural way to think about it. But these aren't exactly circles; it's almost circles. So what we might want to do is we might want to draw a circle on top of it. And an easy way to do that would be to put a couple more points on the circle, or on the spiral, like this. And then once you have 3 points, you know from geometry class that you can always draw a circle, which matches those 3 points. And you can see here for this particular spiral, those 3 points match it pretty well. And I could just go ahead and measure the radius of this, and the radius of that is about the square root of 266. Not important, the actual value of it. But the problem is that if I move closer to the origin with points like this, as the points get further apart, I sort of get a bad representation. That doesn't really look very good. So you might think, well, let's move our points closer and closer together. But won't the circle vanish? Well, let's see. So as we move them closer and closer together, it actually doesn't vanish. You can see it sort of stabilizes, and it stabilizes to a specific circle. And that circle that it stabilizes to, and we get down to, you can think of it the limit, just like the tangent line is the limit of secant lines. Well, this is sort of like a secant circle. And the limit of this secant circle is a tangent circle. It's a circle that's tangent to the curve. It's a circle which fits the curve best, and it's actually called an osculating circle. And the radius of this osculating circle is DTDS, and it is the curvature of the it's the curvature of the curve. So we can see, as if I move around here, as we move out, as our intuition would tell us, the circle gets bigger, but at each point we have sort of this tangent circle. And this idea works for other curves as well. I'm not going to go ahead and show you here, but I think you can imagine that the curvature is the radius of this osculating circle, and it's related to the DTDS vector, which is perpendicular to the unit normal or unit tangent vector.